In the spring of 2025, astronomers scanning the Atlas survey frames noticed something moving far too quickly through the outer solar system, an object whose velocity and trajectory immediately marked it as foreign. Within weeks, observations from telescopes across 3 continents confirmed what orbital mechanics had already whispered. This was no wayward asteroid from the Kuiper belt, no long-period comet returning from the Oort cloud. The eccentricity exceeded 1.0 Dorado. The hyperbolic excess velocity measured over 26 kilometers per second. 3. Atlas had arrived from interstellar space, the third confirmed visitor after Oumuamua's tumbling passage in 2017, and Tua Borisov's classical cometary appearance in 2019. But as observing campaigns intensified through the summer months, something else emerged in the data. Something quieter, stranger, and far more difficult to explain. When astronomers began stacking thousands of CCD frames from ground-based observatories, aligning Hubble Space Telescope sequences with infrared captures from the James Webb Space Telescope, they found it. A faint chain of structures trailing behind the comet's nucleus, maintaining consistent spacing over observation windows spanning many hours. The features were subtle, visible only in deep co-added images where noise had been averaged away and transient artifacts filtered out. Yet they persisted. Knots and arcs in the antitail that moved together, drifting along the comet's trajectory in what appeared to be synchronized motion. A rhythm in the wake that defied the chaotic randomness typically seen in cometary debris streams. Spaceweather.com was among the first to publish annotated images showing the pattern, cautiously noting that the structures appeared phase-locked across multiple observation epochs. Mission science teams remained measured in their language, emphasizing the need for independent confirmation and careful elimination of instrumental effects. But in the stacked data from Hubble's Wide Field Camera 3, in the long wavelength infrared sequences from GWST's NIRCam, and even in amateur photometry shared through collaborative citizen science platforms, the same subtle coherence appeared. This was not a single glitch, not a processing artifact from one telescope's reduction pipeline. It was statistical, reproducible, and deeply strange. 3I, Atlas, had already earned its place in the catalog of cosmic oddities. Its backward-pointing dust structures, grains streaming sunward rather than blown outward by solar radiation pressure, defied conventional tail geometry. Spectroscopy revealed abundant water ice, but water so ancient it bore the isotopic signatures of processing by galactic cosmic rays over billions of years, suggesting a nucleus formed in another star system long before our sun ignited. Color measurements showed an unexpected shift, from reddish hues in the inner coma to a pale, almost ghostly luminosity further out, a transition that standard volatile chemistry could not easily account for. And then there were the metals. Nickel vapor detected at distances where sublimation temperatures should be far too low, hinting at internal heat sources or exotic surface reactions no one had modeled. The synchronized pattern in the wake sat atop this tower of anomalies like a final, quiet challenge. Some researchers framed it as a natural consequence of the comet's rotation, periodic jets shedding clumps of dust and ice at regular intervals, creating a quasi-regular train of features that only became visible when viewed edge-on and stacked over time. Others pointed to plasma instabilities, magnetic field interactions, or resonances between the comet's outgassing and the variable solar wind. A smaller, more speculative group wondered aloud whether the coherence might represent something else entirely. Not debris, but a distributed system of objects moving in formation. The word swarm appeared in a handful of preprints and blog posts, always hedged with caveats, always followed by calls for more data. But it had been spoken, and once spoken, it lingered in the background of every new observation. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. The discovery timeline for 3I Atlas reads like a textbook case in modern sky survey astronomy. The Asteroid Terrestrial Impact Last Alert System, Atlas, flagged the object on May 14, 2025, during routine scans of the ecliptic plane. Its motion was immediately unusual: high proper motion, significant out-of-plane velocity, and a trajectory that, when preliminary orbits were calculated, showed no closed ellipse. Follow-up astrometry from the Pan-STARRS telescopes in Hawaii, the Catalina Skies Survey in Arizona, and ESA's optical ground station in Tenerife tightened the solution within 72 hours. The orbital eccentricity settled at approximately 1.18, a value that, in the language of celestial mechanics, means the object is gravitationally unbound from the Sun and will never return. Hyperbolic orbits are rare but not unknown. Long-period comets occasionally scatter into near-parabolic paths that carry them back into the Oort cloud. And perturbations from passing giant planets can, in principle, eject smaller bodies into interstellar space. But 3I Atlas bore no resemblance to solar system comets in its chemistry or its past trajectory. Backtracking its path through galactic space, accounting for the Sun's motion relative to the local standard of rest, and the gravitational tides of nearby stellar populations, researchers estimated that the comet had been wandering the Milky Way for tens of millions of years, possibly longer. It had survived radiation exposure, micrometeorite erosion, and the slow leaching of volatile ices into the vacuum, arriving at our doorstep as a relic from another epoch of planetary formation. By mid-June 2025, 3 Atlas had crossed the orbit of Jupiter, still inbound, brightening steadily as solar heating began to liberate frozen gases. By late August, it passed within 2 astronomical units of Mars, close enough for orbiters at the red planet to capture oblique imagery and plasma measurements. Perihelion, the point of closest approach to the Sun, occurred on October 27, 2025, at a distance of roughly 0.730, well inside Earth's orbit, but still tens of millions of kilometers from our planet. Closest approach to Earth itself came earlier, in mid-September, at a safe but still considerable distance of approximately 48 million kilometers. Throughout this inbound arc, the comet's activity surged. Its coma expanded, its tail lengthened, and its light curve grew more complex, revealing subtle periodicities consistent with a rotating nucleus tumbling through space. The synchronized motion behind the comet exists within this orbital context. It is not a static feature frozen in space, but a pattern co-moving with 3 Atlas along its hyperbolic trajectory, drifting outward at velocities consistent with dust grains and sublimated gases ejected from the nucleus. When viewed in time-lapse sequences, the structures appear to migrate away from the comet in lockstep, maintaining their relative spacing even as the entire train stretches and fades into the background starfield. Astrometric catalogs from ESA's Gaia mission have been cross-referenced with pre-discovery archival images from Pan-STARRS and early Vera Rubin Observatory commissioning data, searching for any earlier fainter traces of 3 Atlas or associated debris. So far, those searches have yielded only upper limits, suggesting that the comet was either too faint or too far from the ecliptic to be captured in prior surveys. But as more archival data are processed and deeper stacks are built, the possibility remains that we might yet find 3I Atlas in older images, extending its known trajectory further into the past. The detection of the synchronized wake required not one telescope, but a global network operating across wavelengths, time zones, and institutional boundaries. Hubble Space Telescope, humanity's most famous orbiting observatory, provided high-resolution optical imaging of 3I Atlas's nucleus and inner coma, resolving structure down to the scale of tens of kilometers at perihelion and tracking the evolution of jets and active regions on the surface. GBUSD, operating in the infrared, dissected the comet's chemical composition, spectra showing water-ice absorption bands, carbon dioxide emission lines, and the unexpected signatures of refractory organic molecules, possibly polycyclic aromatic hydrocarbons, mixed into the coma. GBUSD's sensitivity to longer wavelengths also revealed something subtle but significant. The outer layers of the nucleus appeared chemically processed, enriched in carbon-rich compounds, and depleted in volatiles consistent with a crust tens of meters deep that had been slowly altered by cosmic ray bombardment over eons. On the ground, the Gemini Observatory in Chile and Hawaii contributed multi-band photometry and spectroscopy, documenting the comet's changing color and tracking the distribution of gas species, carbon monoxide, cyanide radicals, and trace metals around the nucleus. The Atacama Large Millimeter Submillimeter Array, ALMA, searched for molecular emission at millimeter wavelengths, mapping carbon monoxide and carbon dioxide outflows, and checking whether the trailing structures aligned with chemical inhomogeneities or regions of enhanced gas production. So far, those maps show no strong correlation. The synchronized features appear in dust-scattered light, not in molecular emission, suggesting they are composed primarily of solid grains rather than gas clouds. But perhaps the most crucial contribution came from the combination of survey telescopes and amateur observers. Pan-STARRS, with its two 1.8-meter telescopes scanning the sky every night, provided a continuous record of 3 Atlas's brightness and position, capturing subtle variations in its light curve that hinted at periodic behavior. The Vera Rubin Observatory, still in commissioning but already producing science-quality data by late 2025, added deeper, wider field images that placed the comet within a rich astrometric context. And then there were the amateurs, backyard astronomers with CCD cameras and precisely tracked mounts, imaging 3E Atlas night after night, sharing their FITS files through online forums and citizen science projects. When these images were carefully calibrated, aligned, and stacked, they revealed the same faint knots and arcs that professional observatories had found. It was in this convergence, space-based, ground-based, and amateur, that the synchronized motion became statistically undeniable. No single instrument could claim the discovery. It belonged to the network. To understand why the synchronized wake is so puzzling, one must first understand the physics of how comets behave. A comet is not a single object, but a system, a solid nucleus of ice and rock, a surrounding cloud of sublimated gas called the coma, and 2 tails, one made of dust grains pushed by solar radiation pressure, the other composed of ionized gas swept back by the solar wind. When a comet like 3E Atlas approaches the sun, solar heating warms its surface, causing frozen water, carbon dioxide, carbon monoxide, and other volatiles to sublime directly from solid to gas. This outgassing carries in train dust grains, silicates, organics, sometimes even metallic particles, into the coma, where solar photons exert gentle but persistent pressure, pushing the smaller grains away from the sun, and forming the graceful, curved dust tail visible in long-exposure photographs. 3I Atlas follows this basic script, but with significant deviations. Its outgassing is dominated by carbon dioxide rather than water, a common trait in some solar system comets, but unusual for an object that has spent so long in the cold of interstellar space. The presence of ancient water ice, isotopically distinct from solar system water, suggests that the comet's volatile inventory has been partially preserved despite ons of exposure to the ambient radiation field of the galaxy. But that preservation came at a cost. The surface layers have been chemically transformed, polymerized by cosmic rays into a dark, carbon-rich crust that insulates the interior and regulates the rate at which gases escape. This processed crust may be tens of meters thick, with only localized fractures and active regions where fresh ice is exposed to sunlight and sublimates vigorously. The dust dynamics of 3 Atlas are equally complex. Dust grain size determines how strongly radiation pressure acts. Small grains, a few micrometers across, are pushed outward quickly and form the bright, extended tail. Larger grains, tens to hundreds of micrometers, are pushed more slowly and fall behind the nucleus along its orbit, forming a fainter anti-tail that can point toward the sun when geometry and viewing angle align. The backward-pointing dust structures observed around 3 Atlas are likely composed of these larger, weakly accelerated particles, released from the day side of the nucleus, where solar heating is strongest and then slowly drifting sunward relative to the comet's motion. But dust alone does not explain the synchronized pattern. For that, one must consider rotation and jets. Most cometary nuclei are irregular, roughly potato-shaped bodies spinning with periods ranging from hours to days. As the nucleus rotates, active regions, fractures, or patches of exposed ice sweep in and out of sunlight, creating periodic bursts of outgassing that launch discrete clumps of dust and gas into the coma. If 3I Atlas has a rotation period of, say, 8 to 12 hours, and if one or more jets are strongly active, then it could shed material impulses creating a train of clumps that drift away from the nucleus at regular intervals. When viewed from Earth, these clumps might appear as a series of knots maintaining consistent spacing, the synchronized motion detected in stacked images. There is also the plasma physics to consider. The ion tail of a comet is shaped by the interplanetary magnetic field carried by the solar wind. Instabilities in this plasma can produce wave-like structures, co-rotating interaction regions, and disconnection events where the tail breaks off and regrows. Under certain conditions, these plasma phenomena can create coherent, quasi-periodic features that move together along the tail axis. While the synchronized structures behind 3E Atlas appear primarily in dust-scattered light rather than ion emission, there remains the possibility that magnetic forces are organizing the dust in unexpected ways, charging grains and locking them to field lines or modulating their ejection velocities through plasma drag. All of these mechanisms are, in principle, natural. They require no exotic physics, no unmodeled forces, only a sufficiently detailed understanding of cometary activity and the patience to run the simulations with enough fidelity to match the observations. And yet, even with these tools, the data remain difficult to fully reconcile. The anomalies are specific, and they accumulate. First, the backward dust structures. While large, slow-moving grains can produce sunward-pointing features under the right geometry, the degree to which 3I Atlas's dust appears to stream toward the sun is more pronounced than in most solar system comets. All models require strongly asymmetric day-side activity, with jets firing almost perpendicular to the Sun-comet line, and even then the fit is imperfect. Second, the color evolution. Early observations showed the inner coma with a reddish tint, typical of organics and tholins. But as the coma expanded, it brightened into an unexpectedly pale, almost white luminosity. Standard emission mechanisms, resonance fluorescence of water, carbon monoxide or cyanide, do not easily account for this shift, and some researchers have suggested that the comet is scattering sunlight off fine dust in unusual ways, or emitting from molecules that have not yet been identified in the spectra. Third, the metals. Spectroscopy from multiple observatories detected not only the usual sodium and calcium seen in many comets, but also iron and, most surprisingly, nickel vapor at distances where surface temperatures should be far too low for such materials to sublimate. Nickel melts at over 1400 degrees Celsius. Even in vapor form, it requires temperatures well above several hundred degrees to be detectable in significant quantities. One explanation involves nickel tetracarbonyl, a volatile organometallic compound that can form at low temperatures if carbon monoxide and metallic nickel grains coexist in the coma, a process that is chemically plausible but rarely observed. Another explanation invokes internal heat, perhaps from the decay of long-lived radioisotopes or from exothermic chemical reactions within the nucleus. But such heat sources would need to be extraordinarily efficient to reach the surface and drive metal sublimation. And then there's the synchronized motion itself. The spacing between the knots in the anti-tail is roughly consistent, measured at intervals of a few thousand kilometers when projected onto the sky. The light curve shows subtle, correlated oscillations, brightness fluctuations that track, at least loosely, with the apparent drift of those structures. Multiple observation sequences, separated by days or weeks, show the pattern persisting even as the overall tail morphology evolves. This is not random. It is not noise, but neither is it cleanly explained by any single model. Periodic jets can produce clumps, but maintaining such regular spacing over hundreds of thousands of kilometers requires fine-tuned rotation periods, consistent ejection velocities, and minimal disruption from turbulence or solar wind buffeting. Plasma instabilities can produce coherence, but they typically operate on smaller scales and shorter timescales. The data are robust, confirmed across instruments and reduction pipelines, but they sit uncomfortably between conventional explanations. Mass estimates, volatile output rates, and tail morphology are also not mutually consistent. Estimates of the nucleus diameter range from 2 to 4 kilometers, depending on assumptions about albedo and surface roughness. Gas production rates, inferred from spectroscopy, suggest a moderately active comet, Yet the extent of the dust tail implies either a very high dust-to-gas ratio or a population of grains with unusual optical properties. Each measurement, taken individually, is reasonable. Together, they form a portrait that does not quite cohere, suggesting that at least one of the underlying assumptions about composition, structure, or activity is incomplete. When faced with such anomalies, science follows a hierarchy. Start with the simplest, most conservative explanations and only escalate to more exotic hypotheses when the simple ones fail. For 3 Atlas, the most conservative framework remains that of a heavily processed metal-enriched interstellar comet, whose asymmetric jets, layered crust, and unusual volatile mix naturally produce backward dust configurations, strange chemistry, and quasi-regular debris trains. Models invoking large, weakly accelerated dust grains ejected from rotating active regions can, with sufficient parameter tuning, reproduce much of what is observed. If the nucleus is elongated and tumbling, if the active regions are localized to polar caps or equatorial fractures, and if the dust grains are fractal aggregates with complex optical properties, then the apparent anomalies begin to soften into rare but not impossible edge cases. A step up the ladder of complexity brings in more nuanced physics. Charged dust populations interacting with the interplanetary magnetic field, resonances between the comet's spin period and solar wind variability, or cryovolcanic vents that pulse on timescales tied to subsurface pressure cycles. These mechanisms are speculative, but not ruled out by the data. They require additional assumptions, but they remain within the bounds of natural processes observed or theorized in other astrophysical contexts. At the far end of the spectrum lie the exotic interpretations, the proposals that the trailing structures might represent not debris, but a distributed system of objects moving under coordinated dynamics. The term swarm has been used, cautiously and often in quotation marks, to describe the possibility that 3A Atlas is accompanied by smaller bodies or artificial constructs that maintain formation as the comet travels. This idea draws parallels to the debate around Oumuamua, whose non-gravitational acceleration sparked suggestions of light sails or propulsion systems, though subsequent work showed that outgassing from a hydrogen iceberg could explain the hydrogen acceleration naturally. For 3I Atlas, the synchronized motion and the presence of unusual metals like nickel, sometimes associated with industrial processes, have led a small number of researchers to wonder aloud whether we are witnessing something more than geology. But extraordinary claims require extraordinary evidence, and the evidence here, while strange, is not yet extraordinary in that sense. There are no radio signals, no anomalous heat signatures beyond what might be explained by chemical reactions, no obvious violations of physical law. The metals, while unexpected, can be accommodated within models of comet chemistry if one allows for processed crusts and volatile organometallics. The synchronized motion, while striking, is at least partially consistent with periodic jet activity. The history of interstellar object studies teaches humility. Ambiguous data will always attract imaginative interpretations. But the burden of proof lies with those proposing deviations from the null hypothesis. So far, 3I Atlas has not crossed that threshold. As 3I Atlas continues its outbound journey, now beyond Earth's orbit and receding toward the outer solar system, the window for close observation is narrowing, but it has not yet closed. Hubble and JWST will continue to monitor the comet through early 2026, tracking changes in its activity as solar heating wanes and the coma shrinks. JWST's spectroscopic capabilities will be especially valuable if deeper layers of the nucleus are exposed by erosion or fracturing during perihelion, offering a glimpse beneath the processed crust into the pristine ices that have survived since the comet's birth. ESA's JUICE mission, en route to Jupiter, but passing through the inner solar system during 3I Atlas's outbound arc, captured high-resolution imaging and plasma measurements in October 25 by dive. Those data are currently being downlinked and processed, with full release expected in mid-2026. JUICE's instruments include magnetometers and particle detectors that can probe the interaction between the comet's plasma tail and the solar wind, potentially revealing whether magnetic forces play a role in organizing the synchronized structures. Mars orbiters, NASA's MAVEN and ESA's Mars Express, also imaged 3I Atlas during its relatively close passage in August, though at oblique angles and lower resolution. Those images are being analyzed for additional context on the tail morphology and any temporal variability. Looking further ahead, the Vera Rubin Observatory, with its wide-field legacy survey of space and time set to begin full operations in 2026, is expected to detect dozens of new interstellar objects per year, transforming the study of such visitors from anecdotal case studies into statistical science. If the synchronized motion behind 3A Atlas is a signature of common physical processes, periodic jets, resonant instabilities, or fractal dust dynamics, then future interstellar comets should show similar patterns. If it is unique, then 3A Atlas will be remembered not just for what it revealed, but for the questions it left unanswered. Coordinated observing campaigns are already being planned for the comet's continued outbound phase. Repeated imaging sequences, optimized for pattern tracking, polarimetric mapping to distinguish dust scattering from plasma emission, and refined from plasma emission. Light curve analyses searching for phase relationships between brightness oscillations and the drift of structures in the tail. Some teams are also preparing for the possibility of a future, dedicated mission, a fast-response spacecraft capable of intercepting interstellar objects within months of discovery, carrying cameras, spectrometers, and sample return capability. Such a mission remains on the drawing board, but 3 Atlas has made the case for it more compelling. The comet will cross the orbit of Jupiter again in early 2027, by which point it will be faint and difficult to observe even with the largest telescopes. By the time it exits the heliosphere, sometime in the 2030s, it will have faded below the detection threshold of all but the most sensitive instruments. Yet the data it leaves behind, the images, spectra, light curves, and the quietly synchronized pattern in its wake, will continue to be analyzed for years, perhaps decades, as new models are developed and new interstellar visitors provide comparative context. When Oumuamua streaked through the inner solar system in 2017, its strange acceleration and elongated shape ignited debates that still echo in the literature. When Toya Borisov followed in 2019, its near-classical cometary behavior was, paradoxically, almost disappointing, proof that not all interstellar visitors are anomalies. 3I Atlas sits between these extremes, strange enough to demand attention, conventional enough to resist easy sensationalism. Its backward dust structures, processed crust, ancient water ice, unexpected metals, and the quiet rhythm of structures drifting behind it combine into a portrait of an object that is both familiar and foreign. A comet, yes, but one that has traveled farther, endured longer, and carries within its frozen nucleus the chemical memories of another star. Each interstellar visitor is a fragment from elsewhere, a messenger bearing isotopic ratios and molecular inventories that trace back to nebulae and protoplanetary disks now long dispersed. The water in 3I Atlas is older than our sun. The metals were forged in stellar cores that burned and died before Earth coalesced. The organics, those complex carbon chains hinted at in the infrared spectra, may be the same building blocks that seeded life on our own world, scattered across the galaxy by billions of comets like this one, wandering the dark between the stars. The synchronized motion, whatever its origin, stands as a reminder that the universe often hides structure just beneath the noise. It took thousands of images, careful astrometry, and collaboration across continents to reveal it, and even now its meaning remains uncertain. Perhaps it is the signature of rotating jets, shedding dust at intervals dictated by the comet's spin. Perhaps it is a plasma instability, a wave mode in the ion tail that organizes grains into transient coherence. Or perhaps it is something we have not yet imagined, a clue to processes, natural or otherwise, that our models have yet to accommodate. We stand at the beginning of an era when interstellar objects will no longer be rare. The Vera Rubin Observatory alone is projected to catalog 50 or more per decade, each one a new data point, a new test of our understanding. Some will be ordinary, icy bodies ejected from planetary systems much like our own. Some will be strange, and among those strange few, one or two might push our explanations to the breaking point. 3I Atlas, with its quiet anomalies and synchronized wake, may prove to be the exception, an outlier whose peculiarities reflect a unique history of processing and environment. Or it may be the first clear hint of a deeper galactic pattern, a signature repeated across the population of wanderers, visible only to those patient enough to stack the frames and listen for the rhythm beneath the noise. As the comet recedes into the outer dark, trailing its faint chain of knots and carrying its ancient ices back into the void, it leaves us with more questions than answers. And perhaps that is as it should be. The universe does not yield its secrets quickly, nor does it grant easy closure. What it offers instead is the opportunity to observe, to measure, to wonder, and to remain humble before the vastness of what we do not yet know.